All right, let's talk about predicting the unpredictable. I mean, how do you even begin to model events that are rare, totally random, but have a massive impact when they happen? Things like insurance claims, network outages, or, yeah, even huge market crashes. These are the moments that define risk. But what if I told you there's a mathematical tool that can actually find a hidden pattern inside all that chaos? Well, let's find out.
Seriously, think about that for a second. How would you predict a market crash? It's not like these things send you a calendar invite. They seem to come out of absolutely nowhere and can wipe out a fortune in an instant. So how can anyone, from a big shot portfolio manager to you or me, prepare for something that feels completely random? It seems impossible, but is it?
Okay, let's get real and look at some hard data. 16. Over a 6-year period, Bitcoin had 16 major crashes. And by major, I mean the price dropped more than 10% in a single day. These are not just theoretical risks. They are real, painful shocks to the system. And this number is our starting point. It hints that while any one crash is unpredictable, maybe the frequency of these crashes over time, maybe that follows a pattern.
And that is where our hero of the day comes in, the Poisson Distribution. It sounds fancy, I know, but it's a powerful tool named after the French mathematician Simeon Denis Poisson, and it's built for this exact problem, modeling how many times a rare event happens over a set amount of time or space. Now, before you think, oh great, complicated math, hold on. This isn't some brand new concept from another planet. It's actually a super clever, simplified version of a more common tool, the binomial distribution. You see, binomial is great for a set number of trials, like flipping a coin 10 times. But Poisson is for when the opportunities for something to happen are practically infinite, but the chance of it happening in any given moment is teeny tiny. And this is where it gets really beautiful. The whole formula, the whole powerhouse, hinges on just one piece of information. This little symbol right here, lambda. That's just the average number of times the event has happened before. That's it. If you know the average, you can use this to calculate the probability of seeing any other number of events. That Y with an exclamation point at the end, that just means the order doesn't matter. It's all about bridging the gap from past averages to future probabilities.
Okay, so this sounds amazing, right? A magic formula for predicting randomness. But there's a catch. Of course there's a catch. You can't just slap this on anything and everything. Like any good tool, it has an instruction manual. For the Poisson distribution to work its magic, the events you're looking at have to play by a few specific rules. So let's break them down.
There are really just three main conditions. First, the events have to be independent, so one event happening doesn't make another one more or less likely. Second, the average rate, our friend lambda, has to stay constant over time. And third, two events can't happen at the exact same microsecond. It's like car accidents. A crash on one side of town doesn't cause a crash on the other. The city has a stable average number of accidents per day, and you can't have two crashes in the exact same spot at the exact same instant. So it's perfect for things like insurance claims or how many customers walk into a storage hour. Those things are pretty much random and independent. But it is the absolute wrong tool for, say, flipping a coin 20 times. Why? Because you have a fixed number of trials. And it's also not great for things like earthquakes. The main shock might be random, but what about the aftershocks? See? They violate that independence rule.
All right, theory time is over. Let's get back to the main event. Can this elegant little formula actually step into the ring and model the wild, chaotic world of Bitcoin crashes? Well, let's put it to the test with the actual data. And we're not just guessing here. The numbers we're about to look at come from sifting through 6 full years of real-world market data, from the beginning of 2019 to the end of 2024. This is a real stress test for the model. And drumroll please, here it is, the single most important number for our entire model. After crunching the numbers on those 16 crashes over 6 years, we get our lambda 0.193. That's the average number of major Bitcoin crashes per month. I know, it seems like a tiny number, but trust me, this is the engine that's going to power all our predictions. So what do we do with this number? We plug it into the Poisson formula, and suddenly we can turn uncertainty into actual intelligence. We can now ask, what's the probability of a crash next month? The model tells us there's an 82.5% chance of nothing, a nice calm month. But there's also a nearly 16% chance of exactly one crash, and a small but very real 1.5% chance of two. This is how you start to put a number on risk. But here's the million-dollar question. Did the model actually work? Does it match reality? And the answer is, yeah, it worked beautifully. This chart shows it all. The frequencies that our model predicted, for months with 0 crashes, 1 crash, or more, they line up almost perfectly with what was actually observed in the real world. The pattern was there all along, hiding in the randomness.
Okay, so this is a really cool trick for crypto traders. But let's zoom out. Why does this really matter for everyone else? Because this isn't just about crypto. Understanding this tool is fundamental to how we manage risk in pretty much every modern industry. It's about making the unpredictable predictable enough to plan for.
I mean, just look at how widely this thing is used. Banks use it to model how many loans in a huge portfolio might default. Insurance companies use it to forecast how many claims they'll get on any given day so they know to have enough cash on hand. Even retail stores use this to predict customer arrivals. Knowing the odds of 10 people showing up versus 50 in the next hour, that tells them exactly how many cashiers they need. No long lines, no wasted money. Tech companies use it for server failures. Honestly, anywhere you find rare, independent events, you can bet the Poisson distribution is working behind the scenes.
So I'll leave you with this question. Now that you have this powerful way of thinking, what are the rare events in your world that this could help you understand? Maybe it's the number of new sales leads you get each week, or the frequency of bugs in a piece of software. You now have a tool to find that predictable rhythm that's hiding inside all the random noise. Thanks for tuning in.